Hey everybody, I'm Officer Chachi, and today's problem has a bit of a story behind it. So when I was taking pre-calculus, at the very end of the year, our teacher gave us a list of final review questions. She said, if you can solve all of these questions, you should be perfectly fine for the final exam. And this question, or something very similar to it, was on that list. It's a very easy question, but I looked at this problem and I said, okay, I have no idea how to do this. Because even though this problem is very easy to solve, you can solve it way before you take pre-calculus. And in fact, nothing that we had done in pre-calculus is at all relevant to this problem. But what I came up with instead of the very straightforward solution was one that was much more complicated, but I think also very cool. But before we can solve that problem, we need to take a look at the definition of the dot product of two vectors. Suppose we have two vectors, v and w, where v has components a and b, and w has components c and d. Then the dot product of these two vectors is going to be equal to ac plus bd, but it's also going to be equal to the magnitude of v times the magnitude of w times the cosine of the angle in between them, or put another way, it's going to be equal to a squared plus b squared times c squared plus d squared, the square root of both of these expressions, times the cosine of theta, where theta is still the angle between them. So the dot product was something we had actually learned in pre-calc, and when I looked at this problem, after a couple of minutes of what do I do here, my first thought of how to solve this is, well, this actually kind of reminds me of the dot product. Let's take a look at how. Suppose we had two vectors, and one of them is a vector a comma b, right? Well, immediately we know that the magnitude of this vector is going to be equal to the square root of a squared plus b squared. And for the sake of clarity moving forward, we're going to call this vector r. And this is something that we can actually find right away. Because if you're really good with perfect squares, you might notice that 1681 is nothing except for 41 squared. And you can plug this into a calculator very easily. Now, where does this a plus b come in? Well, now we're going to consider a second vector, which we'll call s. And this vector is just going to have components 1 and 1. Well, we actually know the dot product of these two vectors, right? R dot s is equal to, in this case, a times 1 plus b times 1. And that's actually just a plus b, which we already know is equal to 49. Now, all that we need to do to figure out our theta, if we want, is to figure out the magnitude of s, because remember that 49 is equal to the magnitude of r times the magnitude of s times the cosine of the angle in between. And if you have ever heard of your boy Pythagoras, you can already see that this is going to have a magnitude of the square root of 2, and even if you don't know who Pythagoras is, in this day and age, you can still figure it out very easily. You know, it's just 1 squared plus 2 squared is 2, and then you take the square root of that. All very nice and simple. In other words, 49 is equal to 41 times the square root of 2 times the cosine of our theta, where theta is just the angle in between our vector r that we have described here as a and b, and our vector s that we've got over here. In other words, cosine of theta is equal to 49 over 41 root 2. So now let's take it over to the graphical world. We've got our vector s, which is just 1, 1. That is, it's going to just be a line extending from the origin to the point 1, 1. And then we have our vector r. This is not to scale, neither is the other one really, which is going to extend from the origin to point a, b. And we actually know the length of this, right? We know that the length is 41, and we know that the angle between these is our angle theta, where all we know is that the cosine of our mystery theta is equal to 49 over 41/2. So the first time I solved this, I basically said, okay, I've got the cosine of theta, and I'm just going to take this theta, which we already know is pi over 4, or 45 degrees, add it to whatever the inverse cosine of this number is, and then just use that and the magnitude we already have to use, and just using sine and cosine to find A and B. But that's a really bad way of doing it because it's going to be inexact in some ways. So I've actually got a better solution that I'm going to show that is exact, and that's what we're going to take a look at. So note that we actually have two solutions. There's our solution A comma B, and then there's also a corresponding solution of B comma A. Because nothing in our initial problem specified that A is less than B or anything like that. And it should be fairly clear. I think you can believe me when I say that this angle between our vector S and this other vector we can call, I don't know, R prime, although we won't really be thinking of them as vectors moving forward, is also going to be equal to theta, because you could take the exact same dot product and it would have the exact same value. We're just moving in the other direction. In other words, and this is going to seem fairly obvious, the angle between R and R prime is equal to 2 theta. Now here's where things are going to get a little funkier. We want to figure out the distance between A comma B and B comma A in two different ways. First, we're going to use just a basic distance formula, right? Distance is equal to delta x squared plus delta y squared, all raised to the 1/2 power. That is, we're taking the square root of it, which is exactly where the magnitude of a vector comes from anyway. Notice that, well, this side has a length of A minus B, and this side also has a length of A minus B, right? So, in other words, our distance is equal to the square root of, we'll label this B, is equal to the square root of A minus B squared plus A minus B squared, right? And for the sake of argument, we're just going to say that the distance squared is equal to 2 times A minus B squared. You'll see why in a second. It's going to be easier to work with B squared. But we're also going to bring in our trig boy, the law of cosines. In particular, given a triangle where we have this angle theta and these two sides, which we'll call P and Q, the length of this third side is equal to the square root of P squared plus Q squared plus 2PQ cosine of theta. In other words, the D squared is equal to 41 squared plus 41 squared minus 2 times 41 times 41 times the cosine of this angle is just the cosine of 2 theta. And this is an expression we're going to need to toy with a little bit more. So after all of that, we're able to see that D squared is equal to nothing more than 1,922. And if we plug that back into our equation up here, we have 1,922 is equal to 2 times A minus B squared. This means that A minus B squared is equal to 961, and for those of fast arithmetic, you can see that this means that A minus B is equal to 31, and now we can finally solve our equation. Now it's time to actually solve for the exact value of B squared. Well, we already know that D squared equals 41 squared plus 41 squared minus 2 times 41 times 41 times cosine of 2 theta. And what is cosine of 2 theta? Well, you may know from your favorite trig identities that cosine of 2 theta is equal to 2 cosine squared theta minus 1. We're lucky here because we actually know what cosine squared of theta is. remember that cosine of theta is just 49 over 41 over 2. So cosine squared theta is just going to be equal to 49 squared over 2 times 41 squared, right? Now, if we double that, right, so cosine of 2 theta, we're going to just knock off the 2, and then we're going to subtract 1. So we're going to get cosine of 2 theta is equal to 49 squared minus 41 squared over 41 squared, and I hope you can see why that is. Now, returning to this equation, I think you can see that the 41 squared is going to actually cancel out the 41 squared down here. So we've got d squared equals 2 times 41 squared minus, and this is pretty important, 2 times 49 squared minus 41 squared. In other words, d squared is equal to 4 times 41 squared minus 2 times 49 squared. Or sorry, yes, that's correct. Or of course that's just 2 times 41 squared minus 49 squared. Now, this is something we can actually do on paper. We know that 41 squared is 1681. That was one of the first things we showed. And so double that should be equal to 3362, right? And 49 squared we can calculate without too much difficulty as 50 squared minus 49 minus 50. And that's nothing but 2500 minus 99 is 2401. So if we subtract 2401, what we're going to wind up with is just 961. And if we double that, we're going to wind up with 1,922. And we now return to our original system of equations, except I've added one more. I've added what we just showed, that a minus b is equal to 31. If we add our second and third equations together, we'll get 2a equals 80, which means that a equals 40, and that means that, of course, b is equal to 9. And because this is a symmetrical system, the original two equations, you could also have it the other way. You could have it that b equals 40 and a equals 9. And with that, we have solved the system. Thank you so much for watching. If you enjoyed the video, like, comment, subscribe, etc. If you have any problems you'd like me to solve on here, send me the problem and I'll solve it. And until then, stay mathematical. That hashtag stay mathematical. It's a new channel catchphrase.
We're not filming anymore. You can confess all your deepest, darkest secrets.
Well, when I was 5, I
Oh, cut the camera.